Hello, my name is McKenna Croft, and this is my Physics 2212 Lab 3, the magnetic field of a bar magnet. So the purpose of this lab was to measure the distance dependence of the magnetic field due to a small bar magnet and compare measurements to the distance dependence predicted by the equations for the on and off axis magnetic fields derived from the PHYS law, and to simulate the magnetic field of a bar magnet using Python. The main results of the experiment were that the magnitude of the net magnetic field increases as the distance decreases. The magnetic dipole moment is approximately 1.4875 amperes squared, and the measured on-axis magnetic field is 7.45 e-5 teslas. And this stimulated off-axis magnetic field is 2.947 e-5 teslas. So the applied physical principles and models are the PHYS law, which relates the magnetic field in teslas produced by an object at an observation point to the current I running through the object and the distance between the source of the field and the observation point. So the magnetic field for a section is displayed by this equation here, and far from the loop where little r is much greater than big R, and through the center of the loop, the magnitude of the magnetic field of a loop has the shape of the on-axis magnetic field of a dipole, and this is reflected in the equation shown here. And the magnetic dipole moment is equal to the current times pi times the radius squared. The direction of the on-axis magnetic field is the same direction as the magnetic dipole moment, which is the same direction as the conventional current. Some additional key concepts are that the magnitude of the magnetic field of a magnetic dipole on the perpendicular axis is 1/2 the magnetic field of the dipole on axis, or equal to this equation here. And the direction of the perpendicular axis is opposite to the magnetic dipole moment. The magnitude of the magnetic field due to a bar magnet or a magnetic dipole is equal to kr to the n, where k is a combination of magnetic constants, and this is used to solve for the magnetic dipole moment. The general formula for the magnetic field of a magnetic dipole is shown here. So a visual model of the magnetic field is depicted below, where the system is observation point, or the magnetometer, and the surroundings are the bar magnet producing the magnetic field. The assumptions are that there are no other magnetic fields being created apart from the bar, and the magnetometer in the phone is accurate. In the model, we're treating the magnet as a magnetic dipole. So the procedure for this experiment, so the first thing we want to consider is the material. So we're using a bar magnet. Magnetometer is the application, a meter stick, tape, and we're compensating for the magnetic north by orienting the phone such that the magnetometer app has an x component of 0. And then when we measure the on-axis magnetic field, we're measuring the distance between the magnet and the magnetometer, where the magnetometer is on axis to the dipole of the magnet for the following x components of the magnetic field. And there are 3 measurements per magnetic field. And then measuring the off-axis magnetic field, we're measuring the on-axis distance between the magnet and the magnetometer such that the magnitude of the net magnetic field is 100 teslas. And then we're recording the y component in the direction and moving the magnetometer to the new distance. And the new distance is at a 45-degree angle with the x and y components and a z component equal to 0. And then we're measuring the magnetic field at this point in components. And then we're also repeating this procedure 2 times. So for the data analysis, these were our results using the magnetometer application. And this is the data analysis continued with the graph of ln of the magnetic field and ln of r. So the data analysis shows that the following equation is equivalent to the regression line from the data, and the slope of the regression line equals n, and the y-intercept equals ln k. We're solving for k using Euler's constant and the exponential function. Using the constants derived from the regression line, the following equation can be set up to solve for the magnetic dipole moment, and this is shown here. The corrected magnetic field in the y direction was calculated by subtracting the Earth's magnetic field from the measured y component of the magnetic field at the off-axis point. The observations are that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction, and then also as the magnetometer moves closer to the magnet, the measured x component of the. So for the computational model code, the physical constant mu naught over 4 pi was set equal to 1e negative 7 for creating the magnet at the origin. These equations were used, and the magnitude of the magnetic moment was set equal to 1.4875, which matched my original measurements. For creating the function of the magnetic field, this equation was used, and to scale the arrows so they fit on the screen, a b-scale of 600 was used, and a distance of 0.15 was used. And for observation locations on axis and perpendicular to the axis, these vectors were applied. If we were drawing arrows to represent the magnetic field on axis and the magnetic field perpendicular to the axis, these equations were also used. And finally, a d perpendicular was set equal to 0.1413, and for the observation location at 45 degrees from the axis, this vector was applied. And to draw an arrow representing the magnetic field 45 degrees from the axis, these equations were also used. The computational model results showed that as the distance between the magnetometer or observation point and the magnet decreases, the magnitude of the magnetic field increases. At 20 teslas, the distance is equal to 2.16 e negative 1 meters, and at 70 teslas, the distance equals 1.43 e negative 1 meters. The magnetic dipole moment is 1.4875 amperes squared, and the experimental magnetic field off-axis is 3.8 e negative 5 and 2.93 e negative 5, 5.7 e negative 5 teslas. Thus, the magnitude is 7.453 e negative 5 teslas. The simulated magnetic field off-axis is 9.32 e negative 6, 2.80 e negative 5, 0. Thus, the magnitude is 2.95 e negative 5. There is an 86% difference in the magnetic field magnitude between the experimental and the stimulated magnetic field. Possible sources of error that other sources of magnetic fields distorting the measurements, such as nearby light posts and devices like iPhones or iPads, inconsistent placement of the phone or slight movements of the phone during measurements, which lead to inconsistencies in magnetic field measurements. For example, a 1 centimeter change in phone placement causes a shift in the magnetic field measurements by 1 Tesla. The surface not being completely flat, which would interfere with the distance measurements and magnetic field measurements. And then measurement errors with the magnetometer or when determining distance between the magnetometer and the magnet. So if I hadn't oriented my experiment to compensate for the magnetic north and had instead laid out the meter stick at some intermediate angle with respect to Earth's magnetic field. The measured magnetic fields would be different due to not accounting for the magnetic north, because the X components would contribute to the magnetic field measurements, and the Y components would not account for the magnetic north. At an intermediate angle, magnetic north would contribute to both the X and Y components of the magnetic field. Since the magnetometer is laid on a flat surface, the Z component would not change or would see negligible changes. If I were to stick two identical magnets together end to end and run the experiment again, the magnitude of the magnetic field would increase due to the combined magnetic fields from the two magnets, and we would expect the magnitude of the new magnetic field to be approximately double the magnetic field of one magnet due to the law of superposition, and the measured distances for each magnetic field would decrease due to the increased magnetic field magnitude from the two magnets.